Generally speaking, distribution of crude oil through pipelines is one of the most secure methods. However, defects may occur and grow in the pipeline until the pipeline ruptures. Currently, there are inline pipeline assessment devices available that use ultrasonic technology to detect pipeline wall cracks. This equipment is transported inside the pipeline by the flowing crude oil, while at the same time ultrasound measurements are performed. This method can be used to assess up to hundreds of kilometers of pipeline in one run. This figure is a schematic view illustrating such a device. The first pressure vessel A is equipped with batteries that ensure power for several days. A second pressure vessel B contains the electronic component as well as a recording mechanism to store the ultrasound data. Sensor carrier C contains a number of sensor T to ensure the pipe wall is assessed in all directions. In this example, I will show you how to create a computer simulation model that demonstrates how the ultrasound can detect a crack in pipeline. In this figure, the up part shows a sector of a pipeline and a plane A intersecting the pipeline perpendicularly. The lower part shows the enlarged cross-section. The circle represents the steel wall of the pipeline, with the inside filled with petroleum, and the outside surrounded by water. The letter T indicates that there is an ultrasound transducer placed inside the pipe, which emits an ultrasound signal toward the wall and receives the reflected signal. That is, the transducer is operating in pulse echo mode. The rectangular marked as a region of interest is the region that will be simulated in this example. This figure shows the enlarged region of interest. There are three layers of materials: petroleum, steel wall, and surrounding materials, for example, water in this case. This figure is the simulation model, with the region simulated being the same as the region of interest shown in the previous figure. The program used for this example is Wave 2000 Plus, made by CyberLogic. In this 2D model, there are three layers of materials. The top layer is 1 mm of water, the middle layer is 6 mm of steel, and the bottom layer is 6 mm of petroleum. The infinitive boundary conditions are used to simulate the larger region surrounding the region of interest. The figure shows a 2 mm long vertical crack in the steel wall of the pipe. An ultrasound transducer is placed in the petroleum, working in pulse echo mode. For comparison purpose, the same model as the one just described, but without the crack, is also simulated. Here are the simulation results. This figure shows clearly there is a signal that has been propagated to the crack and being reflected back to the receiver transducer. For comparison, the simulation result of a model without a crack is shown in this figure. As may be seen, no signal is reflected back from a crack. To quantitatively measure the reflected signals, this plot shows the time domain signal received from the two simulation models, with and without crack, respectively. The plots show the model with a crack in the pipe has an associated crack signal that appears at about 13 microseconds, and no such signal exists for the simulation model without a crack. This signal strength and shape will be affected by the crack size, shape, position, and orientation, all of which are easy to examine with an appropriate modification to simulation models. If you are interested in running the simulations or creating your own models, you can use Wave 2000 Plus with a free evaluation license. Both the program and the simulation model files can be downloaded from this link. Thank you for watching this video.